Welcome to the third lecture for our Class 12 series of lectures. In this talk, we're going to be discussing how chemists handle mixtures of enantiomers, more specifically, to work with them to perhaps separate them if they want one particular enantiomer over another. So more ideas about stereochemistry and how we work with these compounds and what we might do to make our lives easier in separating them. So let's say, for example, we've got a racemic mixture of this methyl ester. So we have both R and S stereocenters at this carbon. I've not, drawn one or the other. I've just left it ambiguous to indicate that there's a racemic mixture. We haven't gotten to this chemistry yet. This is called a transesterification, so we're going to change the methyl part of this methyl ester to what? To this particular S-methyl benzyl alcohol carbon framework. So you can see we've changed that methyl group out to that S-methyl benzyl alcohol carbon group. And so if we use just a pure enantiomer, so just the S-methyl benzyl alcohol, then what we will produce are esters that are diastereomers. So we have an SS, but then we have an RS. And so the products of that esterification are diastereomers, and those are easily separated because you remember enantiomers have the same physical properties, so they have the same retention time on silica gel. These diastereomers, however, would presumably have different physical properties, different energies, different melting points, boiling points, and also retention on silica, so they could be separated fairly easily. So we're taking advantage of the fact that diastereomers have different physical properties. We're turning our racemic mixtures into pairs of diastereomers. Usually one reactant in such a scheme reacting with a racemic mixture, it has to be chiral. You can't use a racemate for one of the reactants. So for example, here we're doing the same sort of thing, except we've got a carboxylic acid. We have a mixture of R and S that is equal, so a racemic mixture at that stereocenter. This is a carboxylic acid group. This is an amine, which is a Lewis base, so it will be protonated by our carboxylic acid. We use a pure S stereoisomer for our amine, and what we end up with is carboxylate ammonium salts. So a carboxylate alkyl ammonium salt. And those salt pairs, in fact, are diastereomers. So one is S and S, and the other will be S and R. And so you can presumably separate those salts one way or another. Sometimes it's even by looking at crystal morphology. I mean, that's how Louis Pasteur came up with the idea of R and S. He looked at tartaric acid, which are crystals that form at the bottom of wine barrels. It's amazing that he could look at anything straight after getting to the bottom of a wine barrel. At any rate, he found that these crystals were mirror images of each other, and he took a wild guess about what the absolute configuration was for R and S, and he was right. Actually, X-ray crystallography can sort those things out, and many decades later it did, and showed that his initial guess was right. It's amazing what you can work out in your 20s, I guess. Anyways, in theory, you could separate these salt pairs, S and R, S and S, if you wanted to recover, say, for example, the R stereocenter. Then you just add HCl, and you regenerate your carboxylic acid, and presumably you pull away your amine, alkyl ammonium chloride salt, and there you have it. So that's an example of a classical resolution. You'll have to excuse my writing. It kind of went off the tracks on this page. But I think these in general, this particular video in general is just trying to expose you to more ideas about how chemists work with chiral molecules. It would be difficult for me to test you on this material, although I think it's good that you're aware of it, that you know what is out there. Can there be chiral chromatography? And the answer to that is sure. So that's the other physical property that enantiomers have that's different for a given enantiomer. The first we looked at, the way they rotate plane polarized light. The second is the way that they interact with other things that are chiral. So say you have a chiral surface or stationary phase in a chiral column. Say it's set up such that you've got an atom that's bonded to the column, and then it presents at the surface three things coming out, A, B, and C. And let's say A to B to C, it's like a clockwise orientation. Let's say you have a molecule that's chiral. You have R and S stereocenters, and you might have groups A prime, B prime, and C prime. And you can see quite clearly that one of these molecules, the one that has the S stereocenter, where A prime, B prime, and C prime are of the right sort of orientation in order to sort of line up with A, B, and C. Whereas the R stereocenter enantiomer has A prime, B prime, and C prime not so well oriented, so maybe only one of those three groups could line up at any given time. So if these two enantiomers are traveling in the mobile phase, and let's pretend that A prime is sticky to A, and B prime is sticky to B, and C prime is sticky to C, the S enantiomer is going to stay stuck to the stationary phase a lot longer than the R enantiomer. The R enantiomer will come out earlier. And so that's what we see. For our instruments that perform these, chiral chromatography, usually there's a detector which detects our, molecules either using Beer's law and some sort of absorbance detector. And so in time, what we would see is we'd see a couple of peaks if we've got a good program that can separate these stereoisomers on a given chiral column. And so what you'd see is a big peak that corresponds in this case to the R stereocenter stereoisomer coming out first, so earlier in the time axis, and then later our S stereoisomer comes out. And so this is a useful thing for chemists, especially ones who are studying things like chiral catalysts, maybe trying to find reactions that will increase enantiomeric excess. Like if you could develop a chiral catalyst that could produce a given enantiomer in 95% enantiomeric excess, it would be great. So that's the idea behind chiral HPLC. You need a chiral stationary phase for a chiral column to separate enantiomers. It's primarily done on a very small scale, although you could have preparative gram scale quantities separated in this manner these days. Other types of chiral molecules, we can. This is an example of cumulated double bonds. So you have a single carbon that shares two different double bonded carbons. So of course, the geometry around our single carbon is sp, it's linear. This carbon has its hydrogens in the plane of the page. This carbon has one hydrogen coming out of the plane of the page and one going back in. So in allene, you have two planes of symmetry. It's achiral. Let's say you switch one of these hydrogens for a methyl group. Well, you've still got something that has one plane of symmetry. It's chiral. However, if you switch one of these hydrogens for a methyl group, now you have something that's chiral because its mirror image will be non-superimposable. And this takes advantage of hindered rotation around carbon-carbon double bonds. And there are other examples of it, and we'll start our next video on such an example.